Clathrate compounds are a unique class of materials characterized by their cage-like crystal structures, in which guest atoms or molecules are physically trapped within a host framework composed of other atoms, typically forming polyhedral cages. These structures do not involve direct chemical bonding between the host and the guest species, but rather rely on weak van der Waals forces to encapsulate the guest species. Clathrates can be broadly classified into gas hydrates, inorganic clathrates, such as intermetallic clathrates, and organic clathrates, each defined by the nature of their host frameworks and encapsulated guests. One of the most well-known types of clathrates is gas hydrates, in which water molecules form a crystalline lattice that traps gas molecules like methane, ethane, or carbon dioxide. Methane clathrate, also called methane hydrate, is a naturally occurring substance found in ocean floor sediments and permafrost regions. These clathrates are of major interest in energy research due to their vast potential as a future energy resource, with estimates suggesting that global reserves of methane hydrates may exceed those of all conventional fossil fuels combined. However, challenges such as safe extraction methods, environmental impacts, and the risk of destabilization leading to methane release into the atmosphere complicate their industrial exploitation. Inorganic clathrates, particularly silicon-based or germanium-based clathrates, are the subject of significant scientific interest due to their unique combination of electrical conductivity and low thermal conductivity. These materials typically have a framework of group 14 elements, C, Ge, or Sn, often stabilized by alkaline earth or alkali metal atoms occupying the cage interiors. A prominent example is Bar-8 Gar1630, a type I clathrate, where barium atoms are trapped inside a framework made of gallium and germanium. These materials exhibit phone and glass electron crystal behavior, meaning they conduct electricity like a crystal but impede heat flow like a glass. This makes them excellent candidates for thermoelectric applications, where they can be used to convert waste heat into electricity. The development of efficient thermoelectric materials is critical for power generation in space exploration, automotive industries, and other sectors focused on energy efficiency. Clathrate hydrates also play important roles in environmental and climate science. Methane clathrates are believed to have contributed to past climate change events through massive releases of methane, a potent greenhouse gas, from destabilized hydrate reservoirs. Understanding the formation, stability, and dissociation behavior of gas hydrates is essential for modeling future climate scenarios, especially in the context of global warming and melting permafrost. In pharmaceutical sciences, clathrate formation is used to improve the solubility, stability, and bioavailability of certain drugs. Cyclodextrins, cyclic oligosaccharides with hydrophobic cavities, are used to form clathrate-like inclusion complexes with drug molecules, effectively increasing their performance in therapeutic applications. This approach is also employed in the design of controlled-release drug delivery systems and in the stabilization of volatile compounds in fragrances and food additives. Another application of clathrate structures is in gas separation and storage technologies. Clathrate hydrates can selectively trap certain gases based on size and polarity, making them promising materials for applications like carbon capture and storage, CCS, or the purification of natural gas. The ability to form clathrates under specific pressure and temperature conditions allows for controlled gas uptake and release, which can be harnessed in advanced gas handling systems. More exotic uses of clathrates have also been proposed, such as in quantum computing and information storage. Some rare earth clathrate compounds show unusual magnetic or electronic properties, including heavy Fermion behavior, superconductivity, and topological phases. These complex behaviors arise due to the interaction of the guest atoms with the electronic states of the host lattice, offering new opportunities in the design of functional materials for advanced electronic devices. Concrete examples of clathrate compounds include methane hydrate, CH4-5.75H2O, tetrahydrofuran hydrate, C4H8O-17H2O, Bar-8 Gar1630, SR8 Gar1630, Na2 Bar6C46, and U8 Gar1630. Each of these systems illustrates the wide compositional and structural diversity within the class of clathrates. Methane hydrate is important for energy storage and climate modeling. Bar-8 Gar1630 and related intermetallic clathrates are extensively studied for thermoelectric energy harvesting. Cyclodextrine clathrates are used in pharmaceutical and food industries to stabilize bioactive compounds. In conclusion, clathrate compounds represent a versatile and scientifically rich class of materials with broad applications ranging from energy storage and conversion to environmental science, pharmaceuticals, and advanced electronics. Their structural ability to host guest atoms or molecules enables a wide range of functional behaviors that are being actively explored in both fundamental research and applied technological development.